Hi, everyone. My name is Srđan Lukić. I'm with North Carolina State University. I'm a professor in the Electrical and Computer Engineering department, and I will talk to you about batteries today. So this is an overview of the presentation. We'll talk about the components of a battery cell. We'll introduce some terminology about batteries. We'll talk about battery performance metrics. We're going to talk about how we can determine the state of the battery, the state of the charge of the battery or its condition. We'll talk about the battery protection and monitoring requirements. And finally, we'll talk about how we can charge a battery safely. All right, so let's jump in and talk about electrochemical battery cell components. So this is a simple diagram that shows the parts of a battery. We have an equivalent circuit over here of the battery. So a battery has a positive and negative terminal over here. And over here, we can see the physical design of a battery. So we have in a typical battery, like we said, a positive and a negative terminal or a positive and negative electrode. This is the positive and the negative electrode, which correspond to the positive and negative terminal of the equivalent circuit. The positive electrode is also called a cathode, and we'll look at the design of a lead-acid battery cell. So one of the chemistries typically used for batteries is a lead-acid battery. You've also probably heard of lithium-ion batteries and maybe nickel metal hydride batteries. But we'll take the example of a lead-acid battery here and look at that in a little bit more detail. So the cathode of a lead-acid battery is made of lead oxide, and this is the chemical formula for lead oxide. Pb stands for lead, and then O stands for oxide. O2 means we have two oxygen atoms. Then we also have like I said, the negative electrode or the anode. It's made of lead. Between the two electrodes, we have an electrolyte. In the case of a lead-acid battery, that electrolyte is diluted sulfuric acid, and its formula is H2SO4, so that's sulfuric acid. And we have a separator in between the negative and the positive electrode. It basically makes sure that the negative and the positive electrode don't touch each other directly, but rather that a reaction happens at the negative electrode, a reaction happens at the positive electrode, and ions, which frees electrons on one side and ions on the other end, and basically the electrolyte allows the flow and the balancing of charges at both the positive and the negative electrode. So with that, with the understanding of the components of a battery, again, positive and negative electrode, cathode, anode, electrolyte, and separator. Those are the key components. We can see what we can do with the battery. Of course, with the battery, we can charge it or discharge it. If we charge the battery, we would connect a voltage source here. VS stands for that voltage source we connect. If the voltage of that voltage source is larger than the voltage of the battery, current will flow from the voltage source into the battery, and we'll be charging the battery. So we have an ammeter here that measures this current I. So the current will flow into the positive terminal of the battery when it's being charged, but the electrons will actually flow the other way. So the electrons will flow in the opposite direction to the flow of the current. And the current is really just what actually flows through the wire is the electrons, but we use this term called the current to represent the opposite flow of the actual electrons. And then the discharge cycle, we have the opposite, where the voltage of the battery is larger than the voltage of the source. So this is, we would typically connect a charger to the battery, and here we could connect, for example, an electric motor to the battery, or whatever the load may be connected to the battery. So for battery charging and discharging, certain chemical reactions happen. In the case of lead acid battery, in the electrode, in the electrolyte, what we have happening is the sulfuric acid is broken into these hydrogen. Hydrogen is H2, so this is just a free hydrogen with a positive and a negative charge. We will then use this H plus in the electrolyte at the cathode to use up 2 electrons during charging and make this lead sulfate here at the cathode. So this is that we will also produce water at the cathode. So we'll take the hydrogen and the oxygen that's already present in this HSO4, and we will make water, H2O, water. At the anode, what we'll do is we'll release a couple of electrons, and during this charge process, 2 electrons will be consumed at the anode. The opposite happens during discharging. During discharging, we'll release these 2 electrons at the anode, and we will, in the electrolyte, we'll take water and break it into hydrogen and oxygen. And at the cathode, we'll take this O2 over here, negative, and make this lead oxide and SO4 with a negative charge. So basically what we're doing is by when these chemical reactions happen, we will basically free up electrons at the anode during discharge and free up electrons at the cathode during the charge. And as a result, electrons will flow one way or the other to close up this electrical circuit. All right, so we talked about lead acid batteries, but there are many other chemistries we can use. What we basically need is we need, you can see 2 reactions take place, but we need 2 metals, typically metals, and some kind of an electrolyte to basically allow these 2 reactions, one during the charge and another one during discharge. And here's what we have at the positive, typically, like I said, metals at the positive and the negative terminal of the battery. So this is nickel iron, which is also known as nickel metal hydride. Batteries, we have aluminum oxide batteries, we have iron oxide batteries, we have zinc oxide batteries, zinc bromine batteries, zinc chloride batteries. We have molten salt batteries that use sodium sulfur, for example, and some other chemistries here. So basically what we need for a battery is 2 metals and some kind of an electrolyte in between. Like I said, some of the popular batteries we talk about is nickel metal hydride. There are many flavors of that, lead acid, and lithium ion. And again, for lithium ion, there are many flavors of the battery where we use different metals with and different ions to make up the battery. So how these batteries differ is based on their specific energy, and this is theoretical energy. Basically, we want a battery that stores a lot of energy and is very light. That's the ideal battery, and the one we try to design. And as you can see from all these couples, lead acid batteries are not so great. And we'll talk about how we'll talk about this specific energy quite a bit more detail as we go through this presentation. All right. So we talked about the common technologies: lead acid, nickel metal hydride, lithium ion. Now let's look at how we can judge the performance of a battery. So we'll introduce the metrics we'll use to judge the performance of a battery. All right, so I'll call it another way to say that is battery terminology. So we talked about battery cell components. Now we'll talk about the terminology of how we can judge the performance of a battery. All right, what's the first one? Battery capacity. The definition is the amount of charge produced at the negative electrode and consumed at the positive electrode as the battery is being discharged. Energy, we typically measure it in amp hours, released when discharging a battery from a fully charged state until the terminal voltage of the battery drops to its cutoff value. And this cutoff value is determined by the chemistry of the battery. And basically, we define that battery at, that voltage at a value that ensures that the battery doesn't get damaged. If we over discharge the battery, in other words, if we allow the terminal voltage of the battery to go below this cutoff value, we can permanently damage the battery. And the capacity of the battery varies with discharge rate. What that means is if I aggressively discharge the battery, I try to take a lot of current out of the battery in a small amount of time, the battery capacity, or the total amount of electrons we can extract out of the battery, reduces. In other words, we'll reach this cutoff voltage more quickly if we discharge the battery more quickly or at a faster rate. And the reason for that is basically it takes some time for these chemical reactions in here to occur. And if I try to make these reactions happen very, very quickly, these ions don't have enough time to migrate from one terminal to the other, and these reactions can no longer take place within the electrodes. All right, so that's battery capacity. A few other terms we want to define is battery discharge rate. So that's the rate at which we are discharging the battery, right? And you typically call it C rates. So where C is the battery capacity, if I have a 10 amp hour battery, C is 10 is the battery capacity, and H is the discharge time. So if I have a 10 amp hour battery and I discharge it at using 10 amps, the C rate is 1. It's 10 amp hours divided by 10 amps, we get 1. If I have my same 10 amp hour battery and I discharge it at 100 amps, I will have 10 divided by 100. That's called a 10C rate. So I'm discharging the battery at a C rate that's higher than its capacity. And similarly, if I take the 10 amp hour battery and I discharge it at 1 amp, that's called a C over 10 rate. So that's the discharge rate. And then a full discharge is basically a battery is fully discharged when its voltage reaches that cutoff voltage that I discussed earlier. So that's the full discharge rate, and battery capacity are the terms we defined so far. Another term we can define is the state of charge of the battery. That's the present capacity of the battery. So a state of charge of a fully charged battery is 100%. The state of charge of a battery when it reaches the cutoff voltage is 0. And anything in between is some number between those two values. Battery power is another term we want to define. It determines the amount of work done or the energy transferred per unit of time. And basically, the power of the battery is the voltage of the battery at any point in time, multiplied by the current being removed from the battery or discharged from the battery. So that's the battery power. That's an instantaneous quantity. And I can also determine what is the maximum power that I can get out of the battery. and that's determined by the internal resistance of the battery. I can represent the battery as an ideal voltage source in series with some internal resistance of the battery, and that internal resistance can, in a simplified way, be separated into two parts. An ohmic resistance, this is the actual resistance of all the conductors that make up the battery, and this internal resistance that represents the resistance of, or the ability of the battery to quickly allow for that chemical reaction that we talked about that needs to take place at the terminals of the battery. So this internal resistance varies with the rate of discharge. The faster the rate of discharge, the higher the internal resistance. And that's why I have this line through it to show that this is a variable resistance. In any case, if I consider these two values to be constant at some instance in time, R ohm plus R internal, I'll call that R battery. So the maximum power I can extract from the battery is if the resistance I connect to the battery terminals is equal to the internal resistance of the battery, the sum of these two resistors, and that's called the maximum power theorem, where a source, the maximum power that a source, an ideal source, can supply equals the its internal resistance will happen at a resistance, at a load that equals to the internal resistance of that ideal source. So when I do the math, that's what I end up with. The Pmax is Vbat divided by 4 times the internal resistance of the battery. And obviously, from this equation, the smaller the internal resistance of the battery, the higher Pmax becomes. All right, so that's battery power. Can also talk about battery energy, and that's the work done by the battery over a period of time. So that's the integral of the battery voltage multiplied by the battery current. All right, that's some basic terminology. We went through that. Now we want to talk about battery performance metrics. Okay, so we already talked about these reactions that take place in the battery. So these are the usable electrode couples, and in there we talked about the specific energy of the battery. So that's one metric by which we can judge the abilities of a battery or its performance. Here is a more comprehensive list of battery performance metrics. So we talked about the specific energy. That's the energy of the battery divided by its weight. And again, the higher the number, the better. We can talk about peak power of the battery. So we talked about how we calculate the peak power just a second ago. It's that equation V squared over 4R battery. And again, we want that to be as high as possible. I can make a battery that's very energy dense, but there's typically a trade-off between power and energy when we design a battery. We can also talk about the efficiency of the battery. So some energy is lost when the battery is being charged and discharged, and we call that the round-trip efficiency. So if I discharge the battery into the load, I can measure how much energy was transferred to the load. And then if we connect a power supply to the battery and I measure the amount of energy that it was taken to bring the battery back to a full charge, if I take the ratio of those two numbers, that's the round-trip efficiency of the battery. And you can see it's kind of in the 80 or even 95% range, all the way down to 60%. Cycle life is another important metric. So that's how many times I can charge and discharge the battery before it fails. And then also, if I just let a battery sit on a shelf, eventually it'll completely self-discharge. And that's because there's all these chemical reactions that happen in the battery, even when it's not connected to an external circuit. And that's called the self-discharge rate. and that's measured in percent. So it might be a size 6% or, relatively low as 0.6% for lead acid batteries. And then, of course, another important metric is the actual cost of the battery. So I want a cheap battery that doesn't self-discharge, has an infinite life cycle, has a 100% efficiency, has very high power capabilities, and very high specific energy. And of course, there's always going to be a trade-off between these things. So let's see. Why do we like lithium-ion batteries? Well, it has a very good life cycle, very good round-trip efficiency, very good energy density. This table is fairly old, so these numbers are much higher now, actually. This technology has advanced significantly in the last 10 years. Last 10, 20, 30 years, I should say. Certainly last 10 to 20 years. And if I compare that to lead acid batteries, this is the energy density of the lithium-ion batteries. You see it's double lead acid batteries. Now it's more like 10 times higher than lead acid batteries because this technology hasn't advanced much, while lithium-ion batteries have. And the other nice thing, like I said, if you look at the life cycle of lithium-ion batteries, it's in more than 1,000 cycles, 3, 4, 5, 10,000 cycle range, and lead acid batteries, 1,000 is kind of the absolute limit of what a lead acid battery can actually do. Another good thing about lithium-ion batteries, they're getting cheaper and cheaper. And then you can see some exotic chemistries here that have, for example, extremely high specific energy, like zinc air. Typically, air batteries have high specific energy because there's no electrolyte, but they have relatively low cycle life and they're very difficult to make. So we're still, right now, lithium-ion batteries are winning the day, but in the future, we might switch to another chemistry, just like we switched from lead acid to lithium-ion batteries. And one promising technology is lithium air. With lithium air, we can get some really high specific energy numbers, but the chemistry is very volatile, meaning it can explode very easily or it's self-destruct very easily. So it's a technology that's still being developed. Okay, that's on battery performance metrics. Let's move on. So let's look at some interesting properties of batteries, like a battery discharge curve. Again, here we're looking at a single cell of a lead acid battery. If you look at your car battery, it's a 12-volt battery. So in your car battery, you're going to have 6 of these cells in series to get the 12-volt battery, to get the 12-volt design. So as I discharge the battery at different currents, 10 amps, 20 amps, 30 amps, all the way to 100 amps, the capacity that I can get out of the battery reduces. So at a very slow discharge rate, the battery capacity is about 100 amps, 100 amp hours, I'm sorry. And my cutoff voltage is at about 1.8 volts. This is at the voltage at which I have to stop discharging the battery, otherwise I'm going to permanently damage it. If I go to higher discharge rates, I can discharge the battery to lower voltages, all the way down to 1.6 volts per cell, because there's a larger resistive drop in the battery. So I can go to, again, lower voltages without permanently damaging the battery. But an interesting thing happens as I discharge the battery at 100 amps, the capacity I can remove or extract out of the battery goes from 100 amp hours down to 60 amp hours. So the capacity has reduced to approximately half. Okay, so those are battery discharge curves. I can use the Puchert equation to represent this relationship between the battery discharge curve, how the battery discharge curve or the battery capacity varies with the discharge rate. So this is the discharge rate. I, C is the battery capacity, T is time, and K is this Puchert constant. So for an ideal battery, the capacity does not change with the rate of discharge, with the current. The capacity does not change with current I. But in reality, this Puchert coefficient might be in the range of 1.1 to 1.4. For very good batteries, it's kind of in the 1.05 range to 1.1 range. So very high performance lithium-ion batteries are in that range. So let's plot this Puchert equation. If I plot it on a logarithmic scale on the bottom, so each one of these divisions is 10. So this is, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the logarithmic scale. And then this is 10, 20, 30, 40, 50, all the way to 100. So if I put this on the logarithmic scale, that exponential equation that we have here becomes a nice straight line. So this is the Puchert plot for a bunch of batteries that I played around with and I plotted. What's interesting is this Puchert equation kind of stops being exactly true. We stray away from a straight line at very high discharge rates. But this is a very neat and simple way to represent the relationship between battery capacity and rate of discharge. So a neat way to take this complex plot here and represent it just with a single linear line on a logarithmic plot, log by log plot. All right, another cool plot we can make when it comes to batteries is a Ragon plot. It plots battery specific power versus specific energy. Typically in a battery, there's a trade-off between power and energy. I can make a battery that stores a lot of energy, but then it becomes difficult to extract power out of that battery. So each battery design occupies one point on the plot, but a particular chemistry occupies an area of this Ragon plot. So here's an example of a Ragon plot. So on one axis, we have energy density, again on a logarithmic plot, and on another axis, I have the power density. So energy density is watt hours per kilogram, and power density is watts per kilogram. So like we said, I can think of these axes as what is the peak power I can extract out of my energy storage device, battery. And this is for how long can I extract energy out of the battery. So if I am extracting energy out of the battery at a power out of the battery at a very slow rate, I can get a very dense system like a fuel cell that has very high energy density, but I can extract that energy at a very slow rate over here. Then here in the middle, I have lithium-ion batteries, nickel metal hydride batteries, and lead acid batteries. And again, this is not, you can, if you Google Ragon plots, you can find plots that differentiate between these three chemistries. So lead acid batteries are typically kind of all the way down here, and lithium-ion batteries are going kind of towards this edge here. And ideal batteries all the way out of here, I want extremely high energy density and extremely high power density. So lithium-ion batteries are kind of all the way out here, and lead acid batteries are on the low end here. Over here, I have what we call supercapacitor. Supercapacitors, they have very high power density, but very low energy density. And over here, I have some kind of a combination between a battery and a supercapacitor, or ultracapacitor is another name for it. and these are lithium-ion capacitors, and that's a technology that's still in development. So lithium-ion batteries, as you all know, are kind of winning the day right now because they're reasonably high on this plot, they're reasonably inexpensive, and they have a relatively high cycle life, a long life. All right, so Ragon plots, very cool way to compare different battery chemistries. Okay, so these are battery performance metrics is what we talked about. Next, we'll talk about how do we determine the battery condition. Okay, so to ensure that the battery is able to perform its task, we need to know a lot about a battery. And there are three ways to assess the current state of the battery. We call that state of charge, which we already talked about, state of health, and state of function. So state of charge, we already talked about. It can be defined with a simple equation. It's battery capacity, the nominal battery capacity, minus the capacity removed, divided by the battery capacity. So like we said, if the battery is fully charged, the capacity removed is 0. So the state of charge is battery capacity divided by battery capacity. State of charge is 1. When the battery is fully discharged, battery capacity equals capacity removed. So I have a 0 here divided by whatever the capacity is. State of charge is 0. So the removed charge is a function of the discharge rate. So as we showed, the battery capacity is difficult to determine. It depends on how quickly I'm discharging the battery. Battery capacity also changes with the age of the battery. So the capacity of the battery reduces as the battery degrades. And no two batteries are the same. So because this is a chemical device, if I put a little bit more active material in one battery over another one, or the electrode is a little bit thicker in one battery than another, the actual capacity will also change. So with advanced manufacturing processes, these capacity scatter, as it's called, due to manufacturing, reduces, but it can never, like I said, no two batteries are identical. So state of charge tells us a lot about the battery, but not everything we need to know about the battery. So that's why we define the state of health of the battery. So state of health is the ability of battery to store, source, and sink currents and retain charge over extended periods of time relative to its initial or nominal capacity. So the state of health of the battery reduces over time, and its state of health goes from 1 to 0 when the battery is completely failed. So one definition is the one I read. The other one is the remaining functional lifespan of the battery. And a third definition is the ability to deliver the specified performance compared to a fresh battery. It depends on the battery age, current state of charge, how you used it, and its internal resistance. So again, state of health is a very difficult quantity to define, and depending on the application, depending on the manufacturer, this state of health quantity will, or its definition will change. So that's why we have another neat metric we can use, which is the capability state of function of the battery. Does the capability of the battery to perform a specific duty cycle relevant for its functionality in the system that uses the actual battery? It's a function of the state of charge and state of health of the battery. And an example of the battery of state of function is, for example, when you are in an electric vehicle, the vehicle will tell you the state of charge of your battery, but you as the driver of an electric vehicle don't really care about the state of charge of the battery. You care about how many miles can I drive this thing before the battery fails, before the battery is no longer able to move the car. So the state of function in the case of an electric vehicle would be the range of the vehicle. So that's the state of function of a battery in the application of electric vehicle. If I think about my cell phone or my laptop, let's say, in your laptop, you'll get two parameters out of your laptop charger. One is the state of charge of the battery. We talked about that. And the other one is how many minutes can I use this computer before the computer shuts off? And that's the state of function of the battery used in a laptop. So how many minutes before the laptop shuts off? So think about that when you're using a battery powered component. Think about these three metrics and how they come into the picture. All right, let's move on then. How do we actually determine these three metrics? That's an interesting question. So the most precise way to measure the state of charge, state of health, and state of function of the battery is to take my battery and discharge it. It's easy. It's very accurate because I'll know exactly how much current I was able to extract out of the battery. But basically, what I have to do is I have to take my battery out of the system and discharge it, so it cannot be done in a real system. Another way is you just measure how much current I'm taking in and out of the battery, but that system is pretty unreliable, and you can read here why. I can measure the actual electrolyte state. That's very invasive and expensive, and it doesn't work for all the chemistries. I can build some kind of a equivalent model of the battery, and by measuring the voltage and current, basically see what's happening with that model and predict the state of the battery. And then I can do these crazy tests where I inject currents of different currents and voltages of different frequencies into the battery and figure out how it works. And there are many, many other ways to determine the battery condition. Many of them use some kind of intelligence, like machine learning and filtering to basically take quantities I can easily measure, voltage and current, and figure out what is happening with the battery. And that's a very interesting problem that's still being researched. Okay, so next, we talked about the battery, how we determine the battery condition. That's what we talked about. Now we'll talk about how we protect and monitor the battery. All right. So how do we protect and monitor the battery? Well, I have to make sure that I don't overcharge the battery. So I need over voltage protection. I need to make sure I don't over discharge the battery because it can be permanently damaged in both cases. So I need under voltage protection. I need to make sure that I don't over discharge the battery. So if I short the terminals of the battery, I can permanently damage the battery. I can actually make it explode. So I need short circuit protection. Lithium-ion batteries, especially the 20 years ago, if you short them, they would explode. The more advanced designs these days may be able to survive, but really the battery protection system should ensure that there's a fuse somewhere in the system that blows before the current goes very high. So I need short circuit protection. I need thermal protection. I need to make sure that if a battery, there's some kind of a chemical process in the battery that is making it to heat up. I need to know about that. I need a way to sense that. So I need thermal protection. I need a thermal sensor, a temperature sensor within the battery pack to make sure that the battery temperature doesn't go very high. And I need, to know the state of charge, state of health, state of function of the battery. So those are the advanced functions. And then another advanced function is cell equalization. And that typically is a must if I'm connecting batteries in series, unless I have a different way to balance batteries, and we'll talk about that in a minute. So that's what, for example, a generic battery management system looks like. This is a block diagram, what a generic battery management system looks like for an, let's say, an electric vehicle battery, but all the same components you will see in, let's say, your laptop battery. So I have the actual battery. I will monitor the voltage, either of each cell or of the whole pack. I will monitor the current going through it, so I'll know the voltage and the current. That'll be used by the state of charge monitor. I will have a temperature sensor connected to one or more of the batteries. And like I said, I will measure the voltage and the current of the batteries. So the voltage monitors will be used for over voltage and over current protection. The voltage might also be used for the state of charge and state of health monitoring. If I have an over voltage or over current situation, I will open this relay. I will send a fault signal and open the relay. If the state of charge is too low or too high, I will open the relay. If the temperature is too high, I will open the relay. And importantly, if the current is too high, I will open the relay. If the relay is too slow to open when I have an overcurrent situation, I also have a backup fuse in the system here. And I also may have a balancing circuit connected directly to the batteries. And this balancing circuit, I'll talk about a couple of examples of what they might look like. Okay, so cell balancing, why do we need to do it? Without cell balancing or equalizing the voltage of the batteries, individual cell voltages will gradually drift over time, and capacity will decrease. The capacity of the batteries connected in series will decrease over time, and I'll show how that happens. So basically, I want the voltage and the state of charge of batteries connected in series to be the same. And of course, the more cells I have in series, the longer the string, the worse the condition. So here's what that looks like. If I have two cells, two batteries, two battery cells in series, and one has a slightly higher resistance than the other, let's just assume that one has a slightly higher resistance, or let's say slightly lower capacity than the other is a better example, then the cell 2 that has a slightly lower capacity, when I discharge it, will end up here, while the other one will not be discharged as much. Sorry, forget that. If I charge the battery, let's say we're here. If I charge these batteries, they will go up like this. Then they will go down like this. And then they will go up like this. And then if I leave the batteries to rest for 3 months, as shown here, their capacities will diverge. If they have different capacity, let's say they have different self-discharge rates. Then if I do a charge and a discharge, this is what happens. And I let it sit for another 3 months. This is the charge and the discharge. And I let it sit for another 3 months, this is the discharge. So let's see what happened. So here they were kind of almost perfectly in balance. The capacity I can get out of the batteries goes from 0 to 100. And at this very last point here, the capacity I can extract out of the battery goes from 100 only down to 40%. So I only have 60% of usable capacity of the battery as I allow the cells to diverge from each other in terms of their state of charge. And again, I complicated the example too much, but to rephrase that, If I just have two batteries that have a different self-discharge rate, they will slowly diverge as shown here. On the other hand, if I balance these batteries after every use, then you can kind of see that their capacity remains the same over time. So what makes batteries imbalanced? Like we said, no two batteries are the same. They might have different impedance, different self-discharge rates, and then these manufacturing variances cause all kinds of differences in terms of capacity, self-discharge, internal impedance, and so on and so forth. Then I might actually strain, let me not go through this example in too much detail, but if I pack batteries in series, in a pack together, they might heat up more quickly depending on where they are within the battery pack, depending on how the battery is being cooled. So if the temperature of the battery is higher, the self-discharge rate is also higher. Okay, so how do we equalize these batteries? We can use resistive methods, or we can shuffle currents between these batteries. And I'll look at two simple examples that might be interesting for you all to see. One is the resistive method, and that's very simple, right? I charge the battery over here, and I connect a resistor across each battery. This resistor will discharge all of these batteries equally at some discharge rate that exceeds the self-discharge of the battery. So the battery that is at a higher voltage, if these resistors are identical, will have a higher current through its resistor than a battery that's at a lower voltage. So if this is 10 volts divided by 1 ohm, you'll get 10 amps over here. If this battery is at 11 volts and I have 1 ohm here, this current will be 1.1 amp. So slowly over time, this battery that was at a higher voltage at 11 volts compared to this battery that was at 10 volts, because it's being discharged more quickly, this difference will reduce over time. So that's the idea behind this basic dissipative resistor value. So, of course, the larger the resistor, right, the larger the power dissipation of the resistor, the larger the physical resistance is, and the larger the losses on the resistor are. And that's a problem for your system because you're kind of you're just losing charge that way. So the larger the dissipation in these resistors, the better the balancing. But the larger the losses, the more the inefficient this balancing circuit becomes. So rather than just burning off this excess energy, there are neat electrical circuits that can be used that basically take charge from a battery that's at a higher voltage and move it to a battery that's at a lower voltage. And here's a simple example of that. Here I have 3 batteries, and imagine I have these 3 switches here. Each switch can be in one of 2 positions. A top position, as is drawn here, or the bottom position, where the switch would move to this point here, this switch would move to this point here, and this switch would move to this point here. So what do we have here? In this condition here, I have battery 1 connected across capacitor 1 and battery 2 connected across capacitor 2, meaning that the voltage across battery 1 will be the same as the voltage across capacitor 1, and similarly for battery 2 and capacitor 2. When the switch moves to the other position, now battery 2 will be connected across capacitor 1, and battery 3 will be connected across capacitor 2. So if I look at what's happening between battery 1 and battery 2, This capacitor, for some period of time, will be connected across battery 1, and it'll be connected across battery 2 for another period of time. And if there is a difference between battery 1 and battery 2, this capacitor will take charge from one battery and give it to the other. Let's take an example. If this is 11 volts, this capacitor will be charged up to 11 volts. And let's say the voltage of this battery is 10 volts. When I move these switches to this position, this cap is at 11 volts, connected to a battery that's at 10 volts. The capacitor will discharge into the battery, and the voltage of the battery will increase until this capacitor goes down to, let's say, 10.1 volts or whatever voltage this capacitor is able to bring this battery to. Important point, battery voltage is very stable, and a battery capacity is many orders of magnitude larger than the capacity of the capacitor. So the capacitor voltage can change very quickly with a relatively small charge, while it takes quite a bit of current to change the voltage of the battery. So you can see how this capacitor will enable these batteries to be equalized fairly quickly. And you can balance any number of batteries in series by just repeating this building block over and over. Okay, so that's how we can charge batteries, or I'm sorry, that's how we can balance batteries, the voltages of the batteries, using non-dissipative methods. So if these switches are ideal, then there's no losses in here. In reality, these switches are not ideal, but the losses in the switches is significantly lower than the losses in these resistors that we used in the previous design. All right, so that's how we balance batteries. The last thing I'll talk about is how we can actually charge batteries. So how we charge batteries is very specific to the type of battery we are using. So the charging methods will vary depending on the battery chemistries. So nickel metal hydride batteries and lead acid batteries are abuse tolerant. If I overcharge lead acid batteries, as we saw when we looked at the chemical reactions in a battery, when I'm overcharging the battery, and actually it would be fun to go back and look at that. When I'm overcharging batteries, so charging, I will produce, like I said, in the electrolyte hydrogen. So this H2 plus can actually recombine and become H2O if it combines with some electrons. So this will become H2O, hydrogen. And so as I'm overcharging the battery, I'm basically producing hydrogen. And that's why we say lead acid batteries are abuse tolerant. Importantly, when I then discharge the battery, that hydrogen that was produced will combine with this oxygen. And when I have hydrogen and oxygen, I make water. So as long as this hydrogen that was produced when I'm overcharging the battery gets contained within the battery, and I can do that by sealing the battery. That's why often we talk about sealed lead acid batteries. Then I can ensure that the hydrogen stays within the battery, and when I stop overcharging the battery, basically that hydrogen recombines with the oxygen. The problem is, if I overcharge the battery very quickly, I'm going to be producing a lot of hydrogen, and I will build up pressure in this battery, and the battery can explode. That's why these valves, this is why I don't seal the battery, but I have a valve that opens when a particular amount of pressure builds up in this lead acid battery. So again, lead acid batteries are tolerant to overcharge up to a point, and if I'm overcharging the battery, I need to do it at a relatively slow rate so that this hydrogen doesn't build up and there's time for the hydrogen to break up again and instead just make water as shown here. All right. So looking at battery charging methods, lead acid and nickel metal hydrides are abuse tolerant. They're used to break up water and produce heat, and that water can be recombined, or hydrogen can be recombined to make that water again. So on the other hand, lithium-ion batteries can be permanently damaged if you overcharge them, and if you do it very quickly, so they can be permanently damaged because irreversible chemical reactions occur if I keep charging a lithium-ion battery, so their capacity reduces. And more importantly, if I keep a lithium-ion battery charging, it'll eventually explode. It'll heat up and heat up and heat up and explode. So lithium-ion battery chargers have to be designed very carefully where they stop charging the battery when the battery is fully charged. So what does a charging profile of a lead-acid battery look like? So first, we do what's known as constant current charge. So the solid line here is current, and the dashed line is the voltage. As the battery gets charged using this constant current phase, the voltage of the battery increases, right? And this constant current is defined by the manufacturer, and that's the maximum charging current that the manufacturer specifies. When the voltage reaches some predefined value, again defined by the manufacturer, the charger goes from a constant current charging mode into a constant voltage charging mode. In this case, the voltage is maintained at a constant value, and as a result, the current will slowly reduce. So in the case of lead acid battery, we said the current will keep reducing up to, and we'll just keep going down, down, down. So when we reach some minimum current, we are saying that the battery is fully charged. And for lithium-ion batteries, for example, where we follow the same constant current, constant voltage charge profile, we stop here. We end the charge right here. Like I said, you have to your charger has to stop charging, otherwise your lithium-ion battery is going to explode. So it's very important to stop charging when the current reaches some minimum value. In the case of lead-acid batteries, what we do is once we fully charge the battery, we reduce the voltage from a charging voltage to what's known as the floating voltage. And we leave the battery at this floating voltage where the chemical reaction keeps occurring, but the chemical reactions take place so slowly that there's enough time for the produced hydrogen to recombine and make water without the valve opening, the valve of a sealed lead acid battery opening. And basically by floating this battery, we can ensure that the battery self-discharge never occurs and the battery is fully charged. It's also healthy, makes sure that the battery health is improved if it's kept at this floating voltage. So that's very specific to lead acid batteries. All right, so with that, that's all I wanted to tell you about batteries. We talked about a number of things, including, how to, what a battery is made up of, how we can define the battery performance metrics, and how we can talk about batteries, how we can assess the condition of the battery and how complicated that is, what we have to do to protect the battery, and then finally how we can actually charge the battery. Hope you enjoyed this presentation, and thanks for listening.